Hi, welcome to this Blender video tutorial entitled Rigid Bodies Part 4 Constraints. This is the fourth in a series of video tutorials concerning Blender's rigid body dynamics. If you have not viewed the previous tutorials, please do, as they contain information that may not be covered here. Blender's rigid body dynamics can be enhanced using an additional set of controls called rigid body constraints. To demonstrate rigid body constraints, I've placed in my Blender scene a cube object to which, for clarity, I have applied a slight bevel modifier. I will go to Front Orthographic View. Select the cube object, press Shift-D, and make a duplicate object and move it a bit to the side along the X-axis. I'll go to the Scene Editor and invoke the scene's rigid body world by clicking on the Add Rigid Body World button. I'll select the left cube, and in the Rigid Body Tools panel on the left, make it a passive rigid body element. I'll select the right cube and make it an active rigid body element. I'll play the simulation. The active rigid body cube on the right falls down along the Z-axis due to the force of Blender's default gravity. I'll stop the simulation and go back to frame number 1. I'll select both objects, it does not matter in which order, and press on the Constraints Connect button located in the Rigid Body Tools panel on the left. A number of things have happened. First, a constraint has been added connecting the two rigid body objects. As you can see from the new Connect Rigid Bodies panel on the left, the type of connection is fixed, and the location of the connection is center. Second, a new Control Empty object has been automatically added to the scene. If we look at the Outliner panel, this new Control Empty object is named Control Empty. I'll go to Wireframe Display, Z key, and rotate my display a bit, and turn off my 3D Manipulator widget, so that you can see the new Control Empty object. I'll select the Control Empty object, and go to the Physics Editor. Here now is a Rigid Body Constraint panel. This panel's controllers refer to this specific Control Empty object. It shows that the two objects connected by this Control Empty object constraint are a cube and cube.001. I'll click in the Type box and change it to Hinge. Blender's rigid body hinge constraint allows modelers to hinge two connected rigid bodies with a hinge that rotates around the Control Empty object's Z-axis. Currently, the Control Empty object's Z-axis runs up and down, same as the scene's Z-axis. I'll rotate the Control Empty object 90 degrees around the X-axis. Now the Control Empty object's Z-axis runs parallel to the scene's Y-axis. The hinge point is by default centered between the two cube objects. I'll go to Front View. I'll turn off my 3D Manipulator widget, and I'll move the Control Empty object down along the scene's Z-axis so that it rests at the bottom of the cube. I'll then play the simulation. The active cube on the right now falls down due to the force of gravity, but it is hinged to the left passive cube at the point of the Control Empty object. I'll stop the simulation and go to frame number 1. I'll select the Control Empty, and in the Physics Rigid Body Constraints panel, uncheck Disable Collisions checkbox. I'll go back to Solid Shading View, Z key, and I'll play the simulation. The second cube now collides with the first cube. Note that even though the Control Empty object's itself a point in space, the hinge action runs the length of the Control Empty's Z-axis. There's no wobbling or movement along the Control Empty's X or Y axis. I'll stop the simulation and go back to frame number 1. I'll then go to Front Orthographic View. In the Physics Rigid Body Constraints panel for this Control Empty is a Limit Z Angle button along with some controllers. Here we can limit the degrees the hinge will open. I'll activate the limits by clicking on the Z angle button. By default, the controllers are set to lower -45 degrees and upper +45 degrees. These limits, in fact, all rigid body constraint limit types, can be a bit confusing. I'll go to wireframe display. Notice that the positive z-axis of the control empty is pointing toward the front orthographic view. Looking at it from this perspective, the 0 to 360 degree arc of the control empty z-axis runs clockwise to the front view. If we were looking at it from the back view, the 0 to 360 degree arc of the control empty z-axis would run counterclockwise to the back view. It really depends if I had rotated the control empty 90 degrees or -90 degrees around the scene's x-axis. I'll go to front view. I'll set the lower controller to 0 degrees, and I'll set the upper controller to 30 degrees. I'll then play the simulation. The hinge will now open only 30 degrees. I'll stop the simulation and go back to frame number 1. I'll change the upper controller to 90 and then play the simulation. The hinge now opens only 90 degrees. I'll stop the simulation and go back to frame number 1. And I'll go to solid shading display. I'll deactivate the Z angle button so that there is no longer any limits on this hinge constraint and go back to front view. I'll select the second cube and press Shift D and make a duplicate and move it a bit along the x-axis. In the Rigid Body Tools panel, I'll make it an active element. I'll select the second and third cube objects and then press on the Constraints Connect button located in the Rigid Body Tools panel on the left. I'll go to Wireframe View and I'll select the new Control Empty object. I'll rotate it 90 degrees around its x-axis so that the Control Empty's z-axis is parallel to the cube's sides. In front view, I'll lower the Control Empty's object so that it is even with the bottom of the cubes. In the Physics Rigid Body Constraints panel, I'll set the type to hinge. And I'll uncheck the Disable Collisions checkbox. I'll then go back to Solid Shading Display. And I'll play the simulation. The two active cubes are hinged and react to gravity appropriately. I'll stop the simulation and go to frame number 1. I'll go to the Scene Editor and remove the Rigid Body World from this scene by clicking on the Remove Rigid Body World button. I modeled this Rigid Body Dynamics constraint demonstration in a Blender scene named Hinge. I'll switch to a different scene named Spring. Here I have added two slightly beveled cube objects to the scene, one on top of the other. Since this is a different Blender scene, I'll invoke the scene's Rigid Body World by going to the Scene Editor and adding the Rigid Body World. I'll select the top cube and make it a passive element. And I'll select the bottom cube and make it an active element. I'll select both cubes and click on the Connect button in the Rigid Body Constraints panel on the left. It does not matter which order the cubes are selected. I'll go to Wireframe View and I'll select the new Control Empty object. In the Physics Rigid Body Constraints panel, I will change this type to Generic Spring. The generic spring constraint creates a spring-like connection between two rigid bodies. By default, this spring-like action works along all axes, but it can be limited to a specific axis or specific axes. In the Spring Rigid Body Constraint panel, I'll press the Spring Z button and set the spring stiffness to 5. I'll then play the simulation. The lower cube falls down along the z-axis due to the force of gravity, but it springs back upward. I'll stop the simulation and go back to frame number 1. I'll change the spring Z stiffness to 10 and play the simulation. Notice that the higher the spring stiffness setting, the less expansion of the spring effect. I'll stop the simulation and go back to frame number 1. I'll change the spring Z stiffness to 2 and I'll play the simulation. Notice that the lower the spring stiffness setting, the more expansion of the spring effect. I'll stop the simulation and go to frame number 1. I'll go to the scene editor and remove the rigid body world from this scene by clicking on the Remove Rigid Body World button. I modeled this rigid body dynamics constraint demonstration in a Blender scene named Spring. I'll switch to a different scene named Point. Here I have modeled 6 torus objects, 2 cylinder objects, and a UV sphere. All the objects have their origin point in the center of their geometry, and all have their scales applied. As this is a different scene, I'll go to the scene editor and invoke the scene's rigid body dynamics. I'll then select the first torus object and make it a passive rigid body element in the rigid body tool panel on the left. I will in turn select each of the rest of the objects and make them active rigid body elements. I'll then select the first 2 torus objects, and then I'll click on the Connect button in the Rigid Body Tools Constraints panel. I'll then zoom in a bit and select the newly created Control Empty object. In the Physics Rigid Body Constraints panel, I'll change the constraint type to Point. The Point rigid body constraint allows 2 rigid body objects to pivot around a common point. That point is defined by the added Control Empty object. I'll switch to Front View and move the Control Empty object along the x-axis so that it is just outside of the torus object. I'll then select the second torus object and the first cylinder object and click on the Connect button. I will select the new Control Empty object and in the Physics Rigid Body Constraint panel, set the type to Point. I'll then move the Control Empty object along the x-axis so that it is about in the center of where the torus overlaps with the cylinder. I'll select the first cylinder and the third torus objects, and then click on the Connect button. I will select the new Control Empty object, and in the Physics Rigid Body Constraint panel, set the type to Point. I'll then move the Control Empty object along the x-axis so that it is about center of where the torus overlaps with the cylinder. I'll then select the third torus and the fourth torus objects, and click on the Connect button. I'll select the new Control Empty object, and in the Physics Rigid Body Constraint panel, set the type to Point. I'll then move the Control Empty object along the x-axis so that it is just outside of the fourth torus. I'll then select the fourth torus and the second cylinder objects, and I'll click the Connect button. I will select the new Control Empty object, and in the Physics Rigid Body Constraint panel, set the type to Point. I'll then move the Control Empty object along the x-axis so that it is about center of where the torus overlaps with the cylinder. I'll then select the second cylinder and the fifth torus objects, and I'll click the Connect button. I will select the new Control Empty object, and in the Physics Rigid Body Constraint panel, set the type to Point. I'll then move the Control Empty object along the x-axis so that it is about center of where the torus overlaps with the cylinder. I'll then select the fifth and sixth torus objects and click the Connect button. I'll select the new Control Empty object, and in the Physics Rigid Body panel constraints, I'll set the type to point. I'll then move the Control Empty object along the x-axis so that it is outside of the 6 torus object. I'll then select the 6 torus and the UV sphere objects and click the Connect button. I will select the new Control Empty object and in the Physics Rigid Body Constraint panel, but this time I will leave the type set to Fixed. Here I do not want the sphere to pivot about the 6 torus. Rather, I want it to remain fixed to the torus. I'll then move the Control Empty object along the x-axis so that it is outside of the UV sphere. I have now connected all of these objects with constraints. I'll play the simulation. The objects respond to gravity and fall along the z-axis and are connected together with pivot points, allowing each object, except the last fixed torus sphere joint, to pivot about. I will stop the simulation and go to frame number 1. I will add layer 2 to this scene. Here I have a ground plane and 5 stacked cubes. I will select the ground plane and make it a passive element. I'll then select each of the cubes and make them active elements. I will then play the simulation. I'll stop the simulation and go to frame number 1. I will go to the Scene Editor and remove the Rigid Body World from this scene by clicking on the Remove Rigid Body World button. I'll then switch to a different Blender scene named Slider Piston Generic. Here I have modeled 2 cylinder objects, one inside of the other. The lower cylinder terminates in a sphere shape. Here is also an extruded plane object. All of the objects have their origin point located in the center of their geometry. The scale has been applied, and they are rotated about the y-axis on a 45-degree angle. I'll go to the Scene Editor and add a rigid body world to this scene. I'll make the lower cylinder an active element, and I'll set its bounciness to 1. And the plane object, I'll make a passive object and set its bounciness to 1. I want the lower cylinder to slide out of the upper cylinder along the same angle and bounce off the plane object. I'll play the simulation. The lower cylinder falls down along the z-axis. I'll stop the simulation. I will select the lower cylinder and the plane object and click on the Connect button in the Rigid Body Tools panel. I'll then select the new Control Empty object. In the Physics Rigid Body Constraint panel, I will switch this type to Slider. The slider constraint constrains an active rigid body's movement to the direction of the Control Empty's x-axis. I'll rotate the Control Empty 45 degrees about the y-axis. The Control Empty's x-axis now runs along the same plane as the lower cylinder object. In the Control Empty Object's Rigid Body Constraint panel, I will uncheck the Disable Collisions box, and I'll play the simulation. The lower cylinder, whose movement has been constrained to the Control Empty's x-axis, falls down due to the force of gravity and collides with the plane and bounces back. I'll stop the simulation and go to frame number 1. The slider constraint also has a limit function. I will activate this limit function by clicking on the x-axis button in the Physics Rigid Body Constraint panel. Note that the positive x direction of the Control Empty is pointing down and to the right. The upper limit setting affects the movement in the Control Empty's positive direction. The lower limit setting controls movement in the Control Empty's negative direction. I will set the upper limit to 4. This means that the cylinder can only move 4 blender units in the control empty's positive X direction. I'll play the simulation. The lower cylinder stops abruptly after moving 4 blender units along the control empty's positive X direction. I'll stop the simulation and go to frame number 1. I'll also turn off the X-axis limit button. In the Rigid Body Constraints panel, I will change the constraint type from slider to piston. And I'll play the animation. The piston constraint is very similar to the slider constraint. The difference is that the piston constraint constrains both the movement and the rotation to the control empty's X-axis. The piston constraint also has limit controllers for both the X-axis movement and the X-angle rotation. I'll stop the simulation and go back to frame number 1. In the Physics Rigid Body Constraint panel, I will change the constraint type from piston to generic. The generic constraint is much like the piston constraint. The difference is that the rigid body movement and rotation can be constrained along all 3 X, Y, and Z control empty axes. The generic constraint is a bit difficult to use. I'll play the simulation. Note that due to gravity, the lower cylinder falls out of the upper cylinder down along the Z-axis. I'll stop the simulation. In order to set up this constraint so that the lower cylinder only moves along the control empty's X-axis, like when using the slider or piston constraints, I have to activate the Y and Z-axis controls and set both the upper and lower controllers to 0. I then have to activate the X, Y, and Z angle controls and set their upper and lower angles to 0. I can now play the simulation. With these settings, the generic constraint works exactly as the slider constraint.